Welcome to Chemistry with Caroline. In this video, we're going to look at the formation of cyanohydrins and diols. So I have before us here a scheme where we start with a carbonyl compound and we're adding the nucleophile of cyanide, so C triple bond N. It's as a salt here with a sodium spectator ion, and then following that up with dilute acid. Here we have our cyanohydrin, so cyano for this C triple bond N group, and then hydrin for my OH that I'm adding here. If we think about this carbonyl compound, we have a partial negative on the oxygen and a partial positive on the carbon. So the carbon is our electrophilic carbon, and this cyano group is our nucleophile. So if we draw out the mechanism for this, we start with our nucleophile here. It's negatively charged. It's going to be attracted to the electrophilic carbon on the carbonyl compound. It will come in and attack that carbon, and those electrons will get kicked up onto the oxygen there. And so that will give us our cyano group attached and an oxygen with a negative charge. So it would have 3 lone pairs on it there. And then in our second step, we add this dilute acid, and that is going to protonate and neutralize our compound. So this would be considered sort of like the workup step for this reaction. And that protonates the alcohol and gives me the completed neutral product, the cyanohydrin. And we would describe this as a geminal cyanohydrin, geminal meaning that the 2 groups are on the same carbon. The next reaction we're going to look at is the formation of a geminal diol. So again, geminal meaning on the same carbon, and di tells me that I have 2, ol tells me that I have alcohols. So the addition of water to a carbonyl compound will give me a geminal diol. This can be done under acidic or basic conditions. In general, the equilibrium lies towards the reactants. So the carbon-oxygen double bond is more stable than 2 carbon-oxygen single bonds coming off of the same carbon. So we'll go to the next page and we'll look at the mechanism under both acidic and basic conditions. So we'll take a look at acidic conditions first. Under acidic conditions, the first step is always going to be the protonation of that oxygen from the carbonyl compound. So that's going to activate that compound towards attack. So that protonation is going to give me this compound. And we can use equilibrium arrows the whole way here. We've got an acidic condition, so that's going to make the reaction highly reversible because we have a good leaving group no matter what direction we're going because of those protons. So if we think about where we're going, we're trying to get to a diol, which means we need to introduce another equivalent of oxygen there, and that's going to come from water. So in this case, water is the nucleophile. So this water will be attracted to this carbonyl carbon, and those electrons will go on to that oxygen, and that will give me this structure. And then at this point, another water molecule, of which I'm going to have excess if I'm trying to push the equilibrium towards the diol, can come in and deprotonate to give the neutral final product. And I get H3O plus over here, but I'm already in acidic conditions, and that proton is just going to be shuttled around as the reaction is catalyzed by acid. In order to go back in the reverse direction, I could remove water, and that would get me back towards the carbonyl compound. So we can use the Chatelier's principle to try to push this equilibrium in one direction or the other. Under basic conditions, I don't have any protons that can protonate and therefore activate my carbonyl compound. There's nothing acidic in solution, but I do have a much stronger nucleophile in hydroxide as opposed to water. Hydroxide has that full negative charge, so it's going to be attracted to the partially positively charged carbon in the carbonyl compound. It can come in and attack and push those pi electrons up as a lone pair of electrons on the oxygen. This also is a reversible reaction. It's going to be harsher conditions here with this strong base, but the equilibrium does lie towards, again, the carbonyl compound. So that gives me this intermediate structure. And then the best acid that I have in solution is water. Remember, I'm in basic conditions. So under basic conditions, you're going to see negative charges and neutral molecules. Under acidic conditions, you're going to see positive charges and neutral molecules. So this negatively charged oxygen is going to take a proton from the water that will give me that final geminal diol, and then also hydroxide, which is already in solution and can be used as a nucleophile in another reaction. So this has been a look at how to form geminal cyanohydrins and geminal diols. If you found this video helpful, please like, subscribe, and share with your friends. Thanks.